I welcome Thanos. I'm not even going to attempt to pronounce his surname. I'm sure you can do that for me. Thank you very much.
Thank you. Thank you very much. Hello, everyone. I'm Thanos. My surname is Stratikopoulos. I'm from Manchester, and today I have the opportunity to present you our open source framework, TornadoVM, which is a programming framework that allows programmers to accelerate their Java applications on heterogeneous devices like GPUs, multi-core CPUs, and FPGAs. This is the agenda for today's talk. I will start with a little bit of the motivation of our project. Then I will introduce you the insights of TornadoVM. Then highlight a key feature of our system, which is dynamic application reconfiguration. Then some use cases how TornadoVM has been used from applications to extract performance. And finally, the current state and future directions. So let's start with motivation. So why should we care about CPUs, GPUs, FPGAs? And the answer to this question is because they are available. So from our system, from small systems like our smartphones, we have ARM multicores with GPUs. So why not utilize them? Why not exploit all the available hardware that we have in the systems? In data centers, we have seen FPGAs recently being deployed. In the cloud, they have been being available in AWS instances. So starting from a CPU, which is in the left side, we can see an Ice Lake microarchitecture with 8 cores and an integrated GPU. And this microarchitecture can achieve with a GPU, including the GPU, up to 1 teraflop performance, which is good, but it is indicated for control flow execution, so for branches, and for low latency requirements. While if the applications they have a lot of data that can be processed in parallel, they could utilize a GPU, which have high throughput to the memory, and they have available up to 3,000 cores to process data. And lately, it's the FPGA type, which is the nice thing with this chip is that it is reprogrammable. So the same device can be reconfigured and be tailored to the needs that the developer needs. So this is intended for pipelined parallelism and low latency, but it comes at the cost of programmability because they are traditionally programmed by a hardware description language. So despite all this diversity in the hardware that exists and appears in the right part of the slide, the question is how a programmer can harness this, especially from high-level languages like C, C++, even Java. And the answer is by using a programming model, because there is the whole magic. The abstraction comes from the programming model. So in this case, there are programming models for heterogeneous systems like OpenCL and CUDA. And these programming models, they abstract the execution in 2 ways. So they have the principles of the execution model, in which the processor, the CPU, the GPU, and the FPGA, the accelerators, can be used in an abstract form. So the execution is the following. At first, you copy the data into the memory of your device from the RAM, from the main memory of the system. Then you execute, you accelerate the data, and then you copy them out to the main memory. And this way, the CPU, the GPU, and the FPGA, they look alike. They are just accelerators that they process data. So then the question is, OK, we have C++, OpenCL, and CUDA that they can target all the devices available on the systems. But what about managed languages? What about Java, JavaScript, Python? What about languages that they have been designed by nature to write once and run everywhere? Well, the current frameworks, the current JVMs, they emit code for processors, mostly for x86 architecture. Therefore, currently, there is no framework that allows Java transparently to generate dynamic code for any hardware device, like FPGA, GPU integrated transparently to the user. And this is the main motivation of our work. So we envision a system that will allow transparently these languages to exploit all the available hardware on the platform. Let's go and have a look on the insights of TornadoVM. So in this slide, I will present you the software stack in a top-down order. So let's start with the API. Tornado currently doesn't detect parallelism, so it doesn't know which part can be parallelized. So it relies on the programmer to specify that this method could be ideal for acceleration on a GPU. And this is done by exposing our API. So basically, our API is a task-based API. So we have tasks. A task is a representation of a method that could be offloaded on the FPGA or the GPU. And we can have a group of tasks, a group of methods that they could be offloaded and executed on the hardware in a sequence. So then the task, they are forwarded in the runtime, in which we have an optimizer that can optimize the execution. So for example, if we have two tasks, and the second task is consuming data that they come from the first task, then this data, they don't need to be copied out of the GPU. So in this case, we can optimize the data transfers, and we can save energy. And then the runtime emits our bytecodes, Tornado bytecodes, simple bytecodes that orchestrate the execution. The bytecodes are initially executed on the interpreter, and then they are forwarded for lazy compilation into the JIT compiler, which is the Graal compiler, but it has been extended to apply specialization for the devices, for the execution on the FPGA or the GPU. So we have different type of specialization according to the device that we target. And this is essential because although OpenCL can be portable across any device, the performance is not portable at all, especially when you want to run code that is meant to be for GPUs and you target hardware like FPGA, which is ideal for pipeline execution. So then the compiler emits a specialized code, and the code is forwarded to the device drivers, where there is the compiler, for example, the NVIDIA compiler, or for the FPGAs, it can be a high-level synthesis compiler that will compile the OpenCL into the final binary that will be executed and will be offloaded on the device. So our system is modular, and we currently support NVIDIA AMD GPUs. We support CPUs, multi-core CPUs, x86 and AMD, Intel and AMD, and we support also Intel and Xilinx FPGAs. This is now an example of how the user can use TornadoVM, so how he can specify that this code could be parallelized on the hardware, on a GPU, for example. So this is a class, compute, that has one method, the MXM, that computes the matrix multiplication of two arrays, A and B, and the result is stored into the C array. So the only way that the programmer can parallelize the code with TornadoVM is by using the @parallel annotation, which is an annotation exposed to the programmer in order to indicate that these parallels could be parallelized. So this is a hint, and that's all done with the modification of the method. So with this, Tornado is able to parallelize the loops, apply specializations for the hardware devices, and then execute it and get performance for free. The only other change that the programmer needs to do is to be compliant with the API that we expose. So he needs to create a task schedule, which is a group of tasks. In this particular case, it is S0. And this task schedule will have one task in this example because we have one method, T0, the name of the method, and then the parameters of the method. In our interface for the task schedule, we have the stream out, in which the user can specify the variable that will have the result of the actual computation, and then we execute. And once it is compiled, then the programmer can execute the code on the GPU by just running Tornado and then the class name. Tornado is an alias for Java and all the parameters of the JVM that he uses. Let's have a look now into what is dynamic application reconfiguration, which I think is a very nice feature to have in systems. So dynamic application configuration is essentially live task migration. So the tasks, the methods can be dynamically migrated from one device to the other. And this is really cool. Let's have a look into the system, how our framework is built in order to support this functionality. At the top, we have the task schedules, which are the groups of methods to be offloaded on the hardware, to be accelerated. Then Tornado forks one thread per device. So for example, for the multi-core CPU, the integrated CPU, the external GPU, or the FPGA, including a thread for the hotspot, which will JIT compile the code in the OpenJDK. So each thread compiles the code if it is not compiled. And when it is compiled, the code will be stored in the code cache in order to be reused the second time. Then the code is executed, is offloaded on the hardware, and then we're waiting to see when it will finish. So we have a barrier at the end in which all the threads are joined. And after doing that, we are able to apply some policies that we call them. So with these policies, we are able to decide what do we want to do. Do we want, for example, the first thread that will compile and execute to be the only thread that will execute and then kill all the rest? This is the latency policy, which is intended for applications that they are very critical for latency. The other one is the end-to-end, which includes time for compilation and execution. And the other one is peak performance, which is the policy that has only the data transfers in-out and the execution. Let's go to see some performance results of this feature of dynamic reconfiguration. So in this figure, we present 4 systems. TornadoVM is the one that will decide the performance where to be migrated, which is with the dynamic reconfiguration. Then we have the CPU, the GPU, and the FPGA. So in this figure, we have 2 benchmarks, 2 applications. One is the DFT, and the second one is the embody. And we compare 2 different policies, the end-to-end that has the JIT compilation included in the time, and the peak performance, which is the execution and data transfers. The interesting part to see from these results is that for small data sizes, let me first to explain the axis. So the x-axis has the data sizes, and the y-axis is the performance against the hotspot. So we start, and we see that for small data sizes, the performance is ideal. The peak performance can be achieved into hotspot. So it doesn't make sense to get the data, copy them out through PCI Express to the device, and execute small computation because the data are not significantly large. As long as the data sizes increase, we can see that the execution in the GPU or the FPGA, it can be significantly higher than hotspot. Then it makes sense to migrate the execution there. Another interesting fact is, for example, on the peak performance, we can see that if the GPU was not present, so if the pink spots were not present, then the execution for large data sizes would be migrated to FPGAs. And this could be significant because it could give energy savings, significant energy efficiency into the system. The maximum performance that we got is up to 4,500x against the Java sequential code. And that was on the NVIDIA 1060. Let's have a look about how Tornado has been applied in real applications. So, at first I have to say that Tornado is maintained under the umbrella of European Horizon 2020 project, the E2 Data, which has as objective to create an end-to-end solution for big data frameworks that they want to target heterogeneous computing nodes. This is the example of accelerating Apache Flink, which is a big data framework. So in this case, the clients are Java developers that they create operators in Java. They forward the operators into the job manager and the task manager eventually, who will distribute the operators across the available computing nodes on the system, so into the distributed heterogeneous nodes. Each node can have a GPU, can be configured with different hardware capabilities. And this is the goal of this case. In the second case, it's a machine learning acceleration So this use case has been developed by Exus, which is the coordinator of the E2 Data project. And the main problem here is that patients are going to the hospital, they're hospitalized, they are admitted there, and then they are leaving hospitals. But there is a chance that they may be readmitted, depending on the profile, on the disease, the conditions, and other characteristics, other features. So the idea here is to create a machine learning model which will accurately predict how possible it is for a patient to return back to the hospital. So Exus saw that by deploying TornadoVM, they can achieve up to 14 times higher performance for a data set which has 2 million patients data. And the last case that I want to present is a deep learning acceleration. So in this case, we took DeepNets, which is a deep learning framework written in Java. DeepNets currently doesn't have support for GPU acceleration, and we know that deep learning has the potential to be parallelized because it has many networks, many neurals, so it can be processed in parallel. I would like to emphasize here that the current available solutions for deep learning, they are using precompiled kernels, so static binaries that you can deploy also from TensorFlow, and they have bindings for Java, Python. So there's no current framework that can dynamically generate code to the device, for the devices. They're stuck with the static compilers. So on the right side, I have an example of how we accelerated a part of DeepNets for the backward propagation method. So this is the original code of DeepNets. And this is the changes that we did. So we added that parallel annotation. And then we created a task schedule for this particular method, one task. And we specified the input and output of the methods to go to the hardware. So we achieved up to 8 times higher performance for large data sets. Let's have a look on the current state of the project and the future directions that we have. So Tornado currently it is available on GitHub. It is open sourced. So feel free to go to try our examples, to go through the documentation. We have also Docker images available for NVIDIA GPUs and integrated GPUs. I would like to emphasize also that we have tested with any IDE, so you can debug the code for instead of going through the vendor tools, you can use the IDE in order to debug your code in Java instead of using the hardware debuggers and all this painful procedure to develop for FPGAs, for example. So what's next? In the current work, in our work in progress, we were becoming compatible with OpenJDK 11. We are doing optimizations for FPGA and GPU execution. We currently run on AWS instances that they have CPUs, GPUs, and FPGAs. And we're working also on NVIDIA PTX on a CUDA backend. This is our team, composed of academics, staff, and PhD students. And of course, we are looking for collaborations. So feel free to give us feedback, to talk to us. I'm here with Florin, my colleague. So we'd be glad to have a discussion about our project and feedback. And here as takeaways, I would like just to emphasize that our work is not meant to replace Hotspot. We just want to emphasize that the hardware capabilities exist on the hardware, so we may want to leverage for large data sets, so it may worth to offload a part of our program on the FPGA, another part on the GPU, etc. So thanks for your attention. We would be glad to discuss about our project and get some ideas and feedback. So thank you very much.
Any questions? We've got 2 minutes. Sorry. All right, you.
All right, so
Sorry. So you basically schedule the algorithm to one of the hardware stacks that you have, right?
Yes. We don't only schedule, we create the code. So
You create the code.
Yes.
So suppose you. So my question would be, what kind of workloads have you tested this on? Because suppose there's multiple algorithms in parallel. Which one would you optimize, or which one would you run? How would you solve such a problem?
It depends on the characteristics of the application. So it's not a fixed solution. So for example, it's not a specific answer that this will go there.
Yeah.
So GPUs are not intended for pipeline executions, where FPGA can give you more performance improvements there. So I think it's a trade-off, depends on the characteristics of the applications. So at first we profile the code, and then we analyze it. Where to go.
Thank you. One more question, very quick one.
You said you were using the Graal compiler to JIT compile. Were you using Truffle to feed your bytecode into that, or were you feeding it directly?
Good question. So far we don't do that, but it's in the future work in our plans to do that in order to become compatible with any Truffle language.
Thank you very much.
Thank you.